So we're gonna start in a couple minutes, just in case a couple late people ends up showing up. So 2 more minutes. Good morning, everyone. Good to see you here. One last time, maybe. Today is our last regularly scheduled lecture, and whatever we covered today, at the end of it, that's all that's gonna be covered on the final. There's a couple extra topics I would like to cover, but they won't be on the final. And I'll make an announcement on maybe putting up a couple more of these live stream on those particular topics because one is the electromagnetic wave, which is basically what the whole course is building to, and unfortunately we don't have time to cover it. And the other thing is AC circuit. So for all you engineers out there, especially electrical and computer engineers, it's pretty essential before you move on that you get at least a little bit of exposure to AC. So I'll put an announcement about that, and you can watch it anytime during the break, I guess, for your own interest. Anyway, let's move on to today's topic, which is inductors and transformers. The whole thing about inductors is the question of what happens if we connect a coil of wire in a circuit. If we connect the solenoid in the whole circuit, what's going to happen? Well, what we know is that because of this voltage here, we're going to drive a current, right? And this current is going to come around and then go into the coil, right? As a result, you get some voltage, give you some current, gives you some magnetic field, right? Because within the solenoid, your magnetic field depends on the current. So using the right-hand rule, you know that the magnetic field is going to go in that direction. So as the voltage increases, the current increases, the magnetic field increases. But wait, as a result of the magnetic field increasing, then your magnetic flux within the tube, within the solenoid also increases. Therefore, you get some EMF by Faraday's law. Which then, in the end, acts as a voltage to oppose the original voltage that was applied. Lenz's law, right? So then by applying Faraday's law, we have negative and the flux magnetic dt. And as a result of this construction here, because the B is uniform, right, within the solenoid, and across the area, so then this basically becomes d dt, b dot dA, right? All these things pop out, and then you're left with just dB dt, right? Which then gives you, in this case, mu and n, they're both constant, and you're just left with di dt. So in other words, all this thing happens so that as you try to supply a voltage and therefore a current going through the solenoid, what happens is that the solenoid ends up being induced a magnetic field, which then induces an EMF, which then opposes the original voltage, and it's based on the change in the current. Acts as a voltage source right? The bigger di dt is, the faster the current is changing, the bigger this source is going to act. Right, and this is done by inducing an EMF, and that's why we call it, this kind of device, we call it an inductor. And therefore defining this thing called inductance. Most people call this self-inductance. The textbook also covers mutual inductance, which happens to work across different circuit with different loops. We're not going to really go into that. We're going to focus on self-inductance. So take a brief minute here to take a look at this video. I won't show you the whole thing, but the link is in the video description. But the highlight of the video is this right here. So what they had is they have a really big coil there to produce a really big magnetic field. But of course, any coil in a circuit acts like an inductor. So then the focus of this video is coming up right now. Right, this big giant spark. It's because when you turn off the switch, you're having a really big change in the current all of a sudden. So then that big inductor there does whatever it can, creates a huge potential to resist this change, which results in passing the breakdown electric field, dielectric breakdown for air, making that spark. I do invite you to watch the entire video. It's a really wonderful stuff by Physics Girl. She does all kinds of amazing things. So you can think of an inductor as a device that wants to keep the current the same as much as possible. It resists changes in current. And it does so by storing up some energy in a magnetic field. So let's put that all together. So if you have change in current, right, that's going to result in a change in magnetic field. That's going to result in a change in your magnetic flux, right? And all these things has to do with changes, right? Because with Faraday's law, nothing's going to happen if your flux is not changing in time. And this changing flux ends up inducing an EMF, which we can treat as a voltage, right? And then that changes the voltage across the inductor, and then therefore changes the overall current of the circuit yet again. So for a straight long solenoid, which is a preferred shape because the magnetic field is uniform, as we've proved by Ampere's law. I already did most of this in the last slide, but let's just quickly go through it here as well. Magnetic flux. Sometimes I use B or M for magnetic flux. It's totally fine either way, really. So the voltage across is going to be right? And then in this case, your area here, we're talking about the loop of a single loop of the coil, and then the B is in fact perpendicular to that. Therefore, it's all your B is parallel to your DA, and then B is uniform, as we say. So therefore, this reduces quite nicely. So then we're left with d dt of B times A, where B is mu naught big N over L I times the area. Now, which one of these actually changes with time? Well, mu naught's going to change. Mu naught is not changing with time. N doesn't change with time. L doesn't change with time. And the area is fixed, right? So then you are left with that particular expression. And notice there is an n square happening here because the n affects how much magnetic field gets produced, but it also affects how much magnetic flux is working to induce the EMF. And for most coils of wire, right, all these geometric consideration is constant in time. So this becomes a very common kind of expression that, I'm just going to change the notation a little bit, use little l for length, because we'll be defining this other thing called inductance, which is also L. So we end up here at the bottom, something that we can relate with things directly related to the circuit, right? You have potential or voltage, and you have current. So everything else we can encapsulate this here, we can encapsulate and call it inductance. And it's supposed to be constant for a given coil. Right? Doesn't change in time, right? We don't expect it to change. It depends on the geometry of the device, which is not expected to change. And then we give it a unit of henries. So what this allows us to do is allows us to kind of put a black box around all the geometric consideration, similar to how we did for capacitance, right? We worked out based on the area and the distance separating them, what the capacitance, and we just put a thing, we just call that a thing, capacitance, and then we just deal with the circuit that way. Same thing here. For whatever shape, size of the thing, you can calculate this inductance number, and then you can use that as a circuit in the circuit analysis. So that's the governing equation for your inductor, much similar to how the resistor has V equals IR and the capacitor has Q over C. So at this point, usually people have a lot of question about what's the relationship, I guess, what's the similarity and differences between a capacitor and inductance. And in fact, there are some overlap, and it can get a little confusing. Oh, by the way, this is how most inductors look like, right? You have a coil, but not only do you have a coil, usually you have some kind of iron core to magnify the magnetic effect, as we've talked about, right? So usually it's some kind of wire wound around some kind of core. Okay, inductance versus capacitance. Well, there are some similarity and differences, right? So the capacitance builds up a charge Q, and as a result stores the energy in an electric field, right? How it looks like, got some charges this way, builds up a charge, equal and opposite charge, as a result, get some electric field going on the inside, and then we can talk about the energy density and whatever, right? This then creates some kind of delta V based on negative E dot dL, right? We did all that. Governing equation is delta V equals to Q over C. Whereas the inductor, you're not charging it up per se. It's building up a current that goes through it. And once it's established that current, right, it's feeding that magnetic flux, And then by Faraday's law, it tries to maintain that same flux by maintaining that same current. And then how does it do so? It stores up energy in the form of a magnetic field instead of the electric field. And then the V is once again given by Faraday's law. Or sometimes written like this. So as the current would drop, if the current were to drop, then the magnetic field would be induced to keep the current going to resist that change. And so ultimately the governing equation becomes negative L di dt. So to relate these, and then just to take this one more step, yes, they both store energy, they store in different fields, but ultimately the form or the governing equation is what's going to make all the difference here in terms of circuit analysis, is that this one uses the derivative of current, whereas this one uses charge, which is the time integral of the current. And that's going to be a very significant thing as we move forward to analyze these kind of circuit, as well as even if we move on to AC. That's very, very key. Now, and a quick review to find capacitance, right? Given a certain geometry, we assume Q, well, technically plus Q and minus Q on the two conductors. And based on that, we find E. Then we find delta V. Then we find C is equal to delta V over Q. No. My bad. Q over delta V. Whereas, therefore, then the way to find out how big an inductance of a thing is we're going to assume a certain current is going through our coil in a certain direction. That's all totally up to us. Based on that, we can find the B, and we can find the flux, right, once we have the B. Then, now that we got the flux, we take the time derivative of the flux, see what actually depends on time and what doesn't, right? And then finally, to get L, we relate the resulting potential and then divide out the di dt. So in fact, L would then be given by whatever delta V or EMF you find divided by di dt. And then I would hopefully cancel out at that point. And then I already showed you earlier the specific look of the solenoid. Right, this here expression is the inductance of a long straight solenoid. You can treat it as infinitely long, right? Just like our parallel plate capacitor kind of case. Some people express this instead with a little n, so not big N, the total loop, but we have little n, so we're gonna group that together and make little n squared times L, little l for the length, like that. And here, critically, remember how we said that the magnetic field inside the solenoid doesn't depend on the size of the area? But the inductance does depend on the area, because the more area you have, the more flux you have. So that's how you would, that's one type of question, right? Finding inductance, just like how we did with capacitor, right? Given a certain coil geometry, go through these steps, find out that inductance. Then there's a whole slew of other questions that has to do with inductors in circuits, right? Again, similar to the capacitance case, you can do series and parallel combinations, but that doesn't often get done, because for most coils, because you have a substantial amount of wire, there is a certain amount of resistance in there. So it's very rarely you find a circuit with pure only inductors. So we don't really do that too often. But we do have the case of having resistor and inductors in circuits, RL circuits, right? And then remember how when we had RC circuit, we had those funny cases where we would deal with just before, like fully discharged or fully charged or whatever. And then we have the one charging or discharging for that one simple case. Exact same thing we're going to do here. But the wording changed a little bit, because for inductors, we don't say charge and discharge. We say energized and de-energized. But the same kind of keyword applies, right? It's just before or just after the switch got flipped, or after a long time, or whichever it is. This is, of course, all hinging on the governing equation that I've written several times today already, which is this. But the first type of analysis is what happens kind of just before and just after. So when you're fully de-energized and you're energizing, it's like your quote-unquote charging case. So immediately after you like connect it or something, right? In the cases of DC we're going to be dealing with, an inductor likes to keep Actually, that's a general statement, so it likes to keep the same current. Similar to how a capacitor sort of likes to maintain the same voltage. But so right before you flip on the switch, what was the current? The current was 0 because everything was disconnected, right? So we would try to keep the current to be 0. And in fact, because when you flip on a switch like that, right, your V goes from nothing to a whole bunch, right? This slope here is infinite because of the step. So in fact, in the ideal case, all inductor is able to provide as much V as possible to keep the current to be 0. And so in a sense, then we therefore replace with an open switch, similar to a fully charged capacitor. Now, if we go to after a long time, we reach equilibrium of some sort. We'll see how long it takes. But because we're in equilibrium, the current is stable. Somehow, rather. It settles onto some value. It's a stable value. Therefore, di dt is equal to 0. Therefore, delta V will also be equal to 0 because of the governing equation up here. No matter what the inductance is if di dt is 0, then the whole thing would be 0. So with no potential drop, then that's just going to be acting like a wire. So you can see how this inductor thing has like almost the opposite behavior as a capacitor. They're kind of complementary like that. And then if we're de-energizing, so we remove the battery and we only have energized inductor connected with a resistor or something, again, we're doing the simple case of immediately after. Remember what happened with the capacitor, right? The capacitor, when it switches over, it tries to maintain the same voltage that it has before. It can't do that because the charge hasn't changed. Q over C, same Q, same V. For an inductor, it again tries to maintain the same current. So immediately after, because you're flipping a switch again, there's this big vertical step, infinite slope. You can have as much voltage as you need to keep the current the same as before. So based on whatever resistance is in series with the inductor, you can work out how much how much potential it needs to maintain that same current, and it will provide that. So that's again when you have a mixture of resistance and inductor in a circuit in a somewhat complicated looking fashion. We would ask you things like immediately after we switch on the switch. They use some fancy like single pole double throw kind of thing just to avoid momentary disconnect certain things, but effectively it's the same, right? We're looking at immediately after or after a long time, whatever. We replace it with certain simpler components, and then we do Kirchhoff's rule just like before. Very, very similar to RC circuit. And also very similar to RC circuit is we're going to look at the charging and, I just got distracted by the snow outside. We're going to look at the energizing and de-energizing behavior of a simple series RL circuit. And I'm going to just show you how the differential equation gets set up and what result we get. So we're going to again stick with the simplest case where, oh, by the way, this is the symbol for an inductor. So not a jagged squiggly like your resistor, but a bunch of humps, sort of like a coil, I guess. So in this case, if you do the loop rule here, you get plus V minus L di dt minus IR equal to 0. Right? And again, you have this first order linear differential equation with, in this case, the current and the derivative current. So again, we expect our answer to have something like e to the t or something, right? Because you want the thing to look like its own derivative. And the results are as such. This is once again, you can rationalize it as you expect the current to be 0 to start with before you flip on the switch, right? And then eventually it settles down to some kind of maximum current. So then it looks like that. If it starts at 0, you can look at it as having this form here, where in this case tau, if you work it out, it's equal to L over R, right? With the RC circuit, it's simply R times C. This one is L over R. Now the voltage across the inductor, we're going to put an absolute value sign on it because we're just talking about the magnitude. It's going to start high and drop low. Right? It's going to be fully resisting the battery, and then as time goes on, it's going to be weaker and weaker until the current settles into a nice horizontal line, meaning it has no slope, therefore no opposing induced voltage. So that's just a simple T over tau like that. Again, R is all the resistance in series with that inductor. So you can compare this kind of scenario with the RC circuit that we did. Very similar forms. It's just picking the right one and rationalizing whether it starts at 0 and go up to a certain value or start high and go low. So for the de-energizing case, then you just have an inductor. So you just remove the battery, say, somehow. And the thing to remember is that there's a certain amount of current just before the battery got disconnected, and the inductor will try to maintain that same current. So it's going to start high and go low. So in this case, it's going to start at some value and then decay exponentially with the same factor, same tau. Tau, very important here. The voltage, again, is going to start out high and go low. So then this also has this form. So very similar to your RC circuit. Yeah, a nice bout of snow just blew by my window. It kind of stopped now. It's crazy times. Crazy times. So that's how you would that's how you deal with RL circuits. Very, very similar to RC circuits, just picking the right form. Then the next question is, I guess, what happens when you connect a inductor with a capacitor? And we call these RC circuits. So here I have a FET simulation of an RC circuit, an LC circuit. So I'm just gonna really quickly, with this disconnected up here, right? I'm just gonna charge up the capacitor so that we have some energy in here, right? Because if we just connect these two things together with nothing, then nothing's gonna happen. So we have to charge up the capacitor first. Boom. There's a little fire because there's no resistance in between. So I'm going to pause it and we're going to connect this. So what's going to happen is, because there's a positive plate over here, the current is going to be driven through the loop in a counterclockwise fashion, right? So you will see that happen at discharge. Oh, sorry, these are showing electrons, so let's try that again. So we will again charge it up, connect this, and so the electrons would go counter to the current direction, which so means clockwise, right? So it'll go through clockwise and discharge the capacitor as a result, right? But now that the capacitor is discharged, there's a bit of current that's going through the circuit, right? So what the inductor does is tries to maintain that same current. So the current continues to flow. The electrons continue to flow clockwise, therefore charging up the plates in the other way, until the plate gets quote-unquote fully charged again, current stabilizes, the inductor no longer does anything, but now you have a whole bunch of charge built up on the capacitor. So then it pushes the current back the other way. And this cycle, and then it just goes back and forth, right? Let me put a ammeter right here. You'll see that the number goes up, settles, and go the other way, and come back down. If we were to show this on the chart, you can look at the current in the circuit, right? It's going to scribe out some sinusoidal pattern, or you can look at indirectly the charge on the capacitor by looking at the voltage across it, and they'll also provide a sinusoidal pattern. So that's why people sometimes call a simple LC circuit like that as a LC oscillator. The energy just kind of bounce back and forth between these two things. You can think of it as momentarily the energy gets stored in the electrical field in the capacitor, and then later it gets stored in the magnetic field of the inductor, back and forth, back and forth. So that's an LC circuit. So quantitatively, you can kind of picture it like this. So if you go through the loop like that, you can write that you have some kind of charge on your capacitor, Q over C, right, giving you the voltage, minus L di dt equals 0, right? That's the loop. But because we know I is dq dt, therefore we can write this as qc minus L, the second derivative of Q. So we have a second order differential equation, and we end up, and you might have seen this in your, remember this faintly from your simple harmonic motion discussion, but really we're looking for a function that looks just like its second derivative, and these things are sine and cosine functions. There's some initial condition and offset you can put in, but this omega here is given by 1 over the square root of LC. And that's really what we're going to focus on, the oscillation frequency. And then you can apply all the things you learned about harmonic oscillation that you had from 1125 to here. Qmax, of course, refers to the V across the capacitor, right? Because it's just a matter of over C, so then VC does the same thing. Whereas the current, you got a current through the inductor or the whole circuit will be the derivative of such things, so therefore you end up with a cosine dependence. So we end up with an oscillation, and we're really just bouncing the energy between your electric field and magnetic field. And then if we get really crazy, we can dump a resistor in there as well. Right? And we call it LRC circuits. And all that resistor does, it dissipates the energy over time. Dissipates. So if you remember if you have gone there with your 1125 course, you might remember these things called damped harmonic motion. This is exactly what's happening. It's just like a little bit of friction in the system. So then your V over time, they oscillate, right? But then it decays over time exponentially. So, and then it slowly goes to nothing. Drains it all away. We don't go into much further details because, again, you don't know how to solve second order differential equation yet. So there's that. Just kind of qualitatively know how the circuit kind of works. Last topic, transformers. Of course, not this transformer, as cool as he is. The regular, everyday kind of transformer looks a little more mundane and boxy. This is another electronic device, sorry, technically electric device that is quite common, quite useful, and surprisingly easy to analyze. So that's why we dump it in here. So that's a box of it. But the inside, and in fact, inside most of your electronic devices, would have a thing like this. They're basically just coils of wires, kind of arranged in a certain way. What the transformer does is that it converts voltage and or current to different values. But, very quickly, in order for that to work, because it's working through magnetic induction and Faraday's law, the voltage must be changing all the time. If the voltage doesn't change, you're not going to get induction, nothing's going to happen. So that's why transformer is most often used with AC. I mean, there's really complicated way to build transformers for DC when you switch it back and forth, but it's way more complicated than it needs to be. With AC, it's very, very simple because it's already changing all the time. So here's how a transformer will look like. So you have this is an AC source. That's a symbol for it. Because you have a constant dV dt, right? In this circuit, the current, you're going to have some changing current all the time. As a result of this changing current, or as a result of this current, you're going to have a magnetic field, right? But this magnetic field is going to be changing all the time. This magnetic field, wait, let me see if I got the direction right. This magnetic field within this iron core, right? I show you it gets channeled over here, right? And if this is changing all the time, then you're going to have a changing magnetic flux, which then equals to some kind of EMF, which then leads to current within this loop, which then ultimately powers your resistors over here. Now, the amount of current, moving back. Now, the amount of voltage you can get from on this end. Oh, by the way, let's give these some names. You see P and S, we call these primary and secondary. Right? These are just fancy names for which one is the input, which one's the output, right? Which the primary has the input power source hooked onto it. And of course, you see that this setup is completely symmetric, so you can flip it around and use, I guess in this case, the right side as the primary and change the voltage the other way. But, bunch of math later. Actually, not that hard math, but let's just write this down. The voltage across at each end will depend on the number of turns, because the more turns you have on this side, right, the more magnetic field you'll create, but the amount of EMF that gets picked up on the other side will depend on how many loops there is on that side. So the number of turns is what's going to determine how much voltage is going to be on the secondary side based on the primary side. And then the other relation to keep in mind is that assuming an ideal transformer, we're going to say 100% of the power gets moved over. So you can relate the current as well. And really, that's all there is to Transformers. So that's why we dump in here, because it's so dang simple. And I guess that concludes the course. So thank you for your attention and bearing with us through this last little rough patch. If you have any questions, please let me know. Otherwise, I will be posting up. I've already posted up a couple of practice finals. I will make announcements as to the actual format of the final, which is again very similar, and post up the quiz for this one and all the midterm solutions as well. So thank you. Please let me know if you have any questions. That is correct. There's no correction on the midterm, and in fact, the class did very well. Because it is the final and is worth a little bit more, and that you guys have now practice of uploading files online, I think, yeah, I've decided that the final, you'll get 3 hours to do the final of the same length. So same 5 multiple choice, 8 long problem question, which is normally a 2-hour exam. I gave you 3 hours to do it and to upload it. And there's definitely always no corrections on the final. Okay, then I'll sign off. Hopefully, if you're interested, please do show up for those couple bonus lectures, and see you around. Thanks.